Something stopped Google's most powerful quantum computer dead in its tracks. Not a power failure, not a software bug, not human error. It stopped itself at the exact same computational moment every single time they ran the experiment. And when the engineers looked at what it had been calculating in the final microseconds before it halted, they went quiet. That story spread across the internet like wildfire. It was shared millions of times. It showed up in feeds, in comment sections, in group chats late at night. And it tapped into something very deep in the human mind. The suspicion that reality is not what it appears to be. That somewhere, underneath everything we can see and touch and measure, there is something else. Something that doesn't want to be found. But here is where it gets genuinely interesting. Because the real story, the actual documented, peer-reviewed, published in Nature story of what Google's quantum chip has been doing, is in many ways stranger than the viral rumor. It doesn't need to be exaggerated. It doesn't need to be dressed up in mystery or wrapped in science fiction language. What Google has actually built and what they have actually done with it raises questions that physicists, philosophers, and mathematicians have been wrestling with for decades. And those questions do not have clean, comfortable answers. So let's start at the beginning, not with the chip, but with the problem that quantum computing was always trying to solve, the wall that classical computing kept running into, and why breaking through that wall has implications that go far beyond faster computers or better artificial intelligence. Classical computers, the kind in your phone, your laptop, the servers running every website you've ever visited, work by processing information as binary digits, ones and zeros, on or off. Every calculation, no matter how complex, no matter how long it takes, ultimately reduces down to a sequence of switches being flipped. This is not a flaw. It is elegant, reliable, and it has carried human civilization through an extraordinary technological revolution. But it has limits, hard limits, limits baked into the fundamental logic of how those machines think. When physicists began trying to model quantum systems, the behavior of subatomic particles, the interactions between electrons, the dynamics of chemical reactions at the molecular level, they discovered something unsettling. The math describing these systems grew exponentially with the size of the system. Adding one more particle to the simulation didn't add a little more computational load. It doubled it, then doubled it again. The complexity didn't scale linearly. It exploded. And very quickly, even the most powerful classical supercomputers on the planet hit a ceiling. Not a ceiling they could engineer their way past, a fundamental physical mathematical ceiling. Richard Feynman, one of the most brilliant physicists of the 20th century, pointed this out as early as 1981. He said essentially that if you want to simulate nature, if you want to model quantum systems accurately, you need a computer that is itself quantum mechanical. You need a machine that doesn't just represent quantum states with numbers. You need a machine that actually is in quantum states, a machine that doesn't calculate what a particle might do, a machine that, in some sense, becomes the particle. That idea sat mostly in the realm of theory for a long time, because building such a machine is extraordinarily difficult. Quantum states are fragile. They exist in a condition called superposition, where a quantum bit, a qubit, is not just a 1 or a 0. It is both at once, existing across multiple possible states simultaneously, until the moment it is measured and forced to collapse into a single outcome. And that superposition is incredibly sensitive. A vibration, a temperature fluctuation, a stray electromagnetic field. Any of these can destroy the quantum state, introducing errors that cascade through a calculation and render the result meaningless. This is called decoherence. And for decades, decoherence was the enemy. The reason quantum computers kept failing, the reason the dream kept slipping away. Then came Willow. Google's Willow chip is a 105-qubit quantum processor. On paper, that number doesn't sound revolutionary, 105 switches. But qubits are not switches. They are not ones and zeros waiting to be flipped. Each qubit in a superposition state represents a vast space of simultaneous possibilities. And when you entangle multiple qubits, link them together so that the state of one instantly influences the state of another, regardless of distance, you create something that has no equivalent in classical computing. You create a system where the number of states being processed simultaneously grows not linearly, not polynomially, but exponentially. 100 qubits in superposition can, in principle, represent more simultaneous states than there are atoms in the observable universe. But again, decoherence, the errors, the fragility, building a 100-qubit system that actually works, that maintains coherence long enough to complete meaningful calculations, that manages errors without destroying the quantum advantage. This had never been done, not at this scale, not at this fidelity. What Google achieved with Willow, and what they published in Nature in December 2024, was a landmark in error correction. For the first time, they demonstrated that as they scaled up the number of qubits, the error rate went down. Not up, as it had always done before. Down. Below the threshold that theoretical physicists had long said was the barrier between noisy, unreliable quantum systems and the kind of fault-tolerant quantum computing that could actually be useful. This is called the below-threshold regime, and Willow crossed it. To demonstrate this, they ran a benchmark test called random circuit sampling. They asked Willow to process a computational task that has been specifically designed to be easy for a quantum computer, and almost impossibly hard for a classical one, and Willow completed it in under 5 minutes. The same task, run on one of today's fastest classical supercomputers, would take 10 septillion years. That is a 10 followed by 24 zeros. That number is not just bigger than the age of the universe, it is incomprehensibly larger. The age of the universe is roughly 14 billion years. 10 septillion years is 14 billion universes worth of time, multiplied by another billion, and then some. Hartmut Neven, the founder of Google Quantum AI, made a comment in the announcement that lit the internet on fire. He said that this performance, this achievement that so radically exceeds what any classical system could do, lends credence to the idea that quantum computation occurs in many parallel universes. He was invoking a concept proposed by the physicist David Deutsch, who argued in the 1990s that the extraordinary computational power of quantum systems can only be fully explained if those systems are, in some sense, performing calculations across multiple branches of reality simultaneously. That quantum computers are not just fast. They are borrowing processing power from other versions of the universe. Now, it is important to be precise here, because this is where the science and the sensationalism begin to diverge. Neven was not making a formal scientific claim. He was invoking an interpretation. And interpretations of quantum mechanics are not the same as results. The many worlds interpretation, the idea that every quantum event causes the universe to branch into multiple versions, each one equally real, is a legitimate and serious framework within theoretical physics. It was proposed by Hugh Everett in the 1950s. It has been developed and defended by serious scientists for decades. But it is one interpretation among several. The Copenhagen interpretation, which is older and arguably more widely taught, says that quantum superpositions are not multiple realities existing simultaneously. They are probability distributions that collapse into a single outcome upon measurement. The math works out the same either way. The results are identical. The difference is philosophical. What this means is that Willow's benchmark result is real. The computational achievement is real. The error correction breakthrough is real. The claim that this proves quantum computers are drawing power from parallel universes is a philosophical position, not an experimental conclusion. A physicist can look at those results and, depending on their interpretation of quantum mechanics, either see evidence for the multiverse or see nothing of the sort. Both readings are consistent with the data. But here's the thing. Saying that is not the same as saying the result is unimportant. Because even setting aside the multiverse debate entirely, what Willow did with that computation is genuinely extraordinary, and it was not the last extraordinary thing it did. In August 2025, a team of researchers from the Technical University of Munich, Princeton University, and Google Quantum AI published another paper in Nature. This one was different. The random circuit sampling benchmark had been a demonstration of raw power, proof that the machine could outperform classical systems. But it was, in the words of critics, a task designed specifically to make quantum computers look good, with no direct practical application. This new experiment was something else entirely. This was physics. Real, substantive, fundamental physics being done on a quantum processor for the first time. The experiment involves simulating gauge theories. Now, that phrase sounds technical, and it is, but the concept it points toward is one of the deepest in all of science. Gauge theories are the mathematical framework that describes the fundamental forces of nature. The strong nuclear force, the one that binds quarks together to form protons and neutrons. Quantum electrodynamics, which describes how light and matter interact. These are not abstract mathematical constructs. They are the actual operating instructions of the physical universe. They describe why matter holds together, why atoms exist, why anything at all persists from one moment to the next rather than dissolving into chaos. One of the most important features of gauge theories is something physicists call confinement. When two quarks are pulled apart from each other, the force between them does not weaken with distance the way gravity or electromagnetism does. Instead, it stays constant. And as they are pulled further apart, the energy stored in the field between them increases until it becomes energetically favorable for a new pair of particles to spontaneously appear from the vacuum, splitting the field rather than allowing the quarks to separate. This creates what physicists sometimes call a string of force between the particles, an invisible thread of energy that holds them together and cannot be broken without creating new matter. Simulating this on a classical computer is nightmarishly difficult. The mathematics of confinement and gauge theories is some of the most computationally demanding in all of physics. It is a problem that has consumed entire supercomputer clusters for decades. And yet, on Willow, the team was able to simulate these interactions directly. They watched the strings form, they watched them fluctuate, they watched them break. Not as a mathematical approximation, not as a simplified model, but as a direct quantum simulation of the underlying physics. The quantum processor was not calculating what a gauge theory predicts. It was, in a very real sense, enacting the gauge theory. Becoming a small-scale version of the physics it was designed to study. This is what Feynman was talking about in 1981. This is the vision he had. A quantum computer that doesn't simulate nature from the outside using numbers and algorithms. A quantum computer that simulates nature from the inside, using the same quantum mechanical rules that nature itself runs on. And in August 2025, that vision was realized for the first time in a meaningful way. Not completely, not at the scale needed to answer the deepest questions in physics. But unmistakably, for the first time, the door opened. And then, just weeks later, another team reported something even stranger. Using Willow's quantum processor, they observed a phase of matter that had never been seen before in any experiment. Not just a phase that hadn't been observed in this context, a genuinely new phase of matter that had only ever existed in theoretical equations, something called a Floquet topologically ordered state. A non-equilibrium quantum state in a system whose governing rules change over time in a repeating, predictable cycle. Think of it as a kind of quantum material that doesn't obey the usual laws of equilibrium thermodynamics, a material that exists in a rhythm, a material that is perpetually in motion and perpetually structured at the same time. The existence of this phase had been predicted years ago, but the equipment to produce and observe it had not existed until now. And the significance goes beyond the discovery itself, because topological phases of matter are not just scientifically interesting. They are practically important. They are the theoretical foundation for topological quantum computing, a paradigm that would allow quantum information to be stored and processed in ways that are inherently resistant to the kind of decoherence that has plagued quantum systems since the beginning. If topological quantum computing can be realized, it would represent a leap in reliability and stability that makes everything that came before it look like a prototype. So when the viral claims spread that Google's quantum chip was asked to simulate the universe and stopped at the exact same moment every single time, people were ready to believe it, because the real story had already been seeding the ground. People had been hearing for months that this chip had done things classical computers cannot do, that it had probed the structure of reality, that it had touched the fundamental forces, that it had revealed phases of matter no one had ever seen. And into that primed imagination, a dramatic, mysterious, unverifiable story landed like a match in dry grass. The story is false. There is no scientific paper. There is no Google statement. There is no credible journalist, physicist, or institution that reported it. It appears to have originated from a YouTube video and spread through the same ecosystems that have always spread dramatic, unverifiable science content, because dramatic and unverifiable is more shareable than accurate and nuanced. The human brain is not wired to find careful qualification as engaging as a sudden, inexplicable halt at the boundary of the universe. But here's the deeper question the story forces us to ask. Not whether Willow stopped at the same moment every time. It didn't in any documented sense. But whether there is, somewhere in the math of what quantum computers are doing, something that might one day resemble that. A boundary, a limit, a point beyond which computation cannot go. Because that question is not crazy. That question is, in fact, one of the most serious in theoretical physics. There is a concept proposed by physicist Jacob Bekenstein, and later expanded by Stephen Hawking, concerning what is called the Bekenstein bound. It is a theoretical limit on the amount of information that can be stored within a finite region of space with a finite amount of energy. It suggests that information in the universe is not infinite, it is bounded. Every cubic meter of space can only contain so much information. Every system of particles can only encode so many bits of data. Reality, in other words, is not arbitrarily detailed. It has a resolution, it has a limit, and this is not a fringe idea. This is mathematics that sits at the intersection of general relativity, thermodynamics, and quantum field theory. It is taken seriously by the most careful theorists in the world, and it implies something deeply strange when you follow it to its logical conclusion. And if you try to simulate a region of reality on any computer, quantum or classical, you eventually hit that limit, because the information required to perfectly simulate a system grows with the complexity of the system. At some point, the simulation requires more information than the system being simulated actually contains, and at that point, the simulation is no longer a simulation. It is the thing itself. This sounds like philosophy, but it has mathematical teeth. And some physicists take it very seriously as a constraint on what computation, any computation, can ultimately do. There is a related idea, even more radical, proposed by physicist John Wheeler, who coined the phrase that has haunted theoretical physics for decades: it from bit. Wheeler argued that at its deepest level, the universe is not made of matter. It is not made of energy, it is made of information. That every particle, every force, every interaction, every moment of time is ultimately an act of information processing. That the universe is not just something that can be simulated. The universe is a simulation, not in the science fiction sense of a computer running somewhere outside of reality, but in the mathematical sense that the laws of physics are computational rules, and the history of the universe is the output of those rules running from initial conditions to the present moment. If that is true, and it is a serious position held by serious scientists, then asking a quantum computer to simulate the universe is not a metaphor. It is a genuine act of recursion. You are asking the universe, using a small part of itself, to model itself. And the question of whether such a recursion can complete or whether it must inevitably hit a wall is not obviously answerable. This is where the conversation between physics and computer science gets genuinely vertiginous. Because in computer science, there is a concept called the halting problem, proven by Alan Turing in 1936. Turing showed that there is no general algorithm that can determine, for an arbitrary program, whether that program will ever stop running or whether it will run forever. The halting problem is undecidable. There are some programs about which you simply cannot know in advance whether they terminate. You have to run them and see. If the universe is, in some sense, running a computation, if the laws of physics are a program and the history of the universe is that program's execution, then the question of whether that computation will eventually terminate is itself undecidable by any system contained within it, including us, including our quantum computers, including Willow. So in a strange, recursive, philosophical sense, the viral story, as fabricated as it is, points at a real cliff edge. Not a cliff that Willow has reached, not a cliff that any current or near-future quantum computer will reach, but a cliff that the mathematics of computation, the physics of information, seem to agree exists somewhere. A place where calculation confronts its own limits, where the act of modeling reality begins to loop back on itself in ways that cannot be resolved from inside the loop. What Google has built is not a machine that touched that cliff. What Google has built is a machine that proved for the first time that the road to that cliff can actually be traveled, that quantum systems can be controlled, scaled, and run with enough fidelity to do real physics, to simulate the fundamental forces, to reveal new phases of matter, to outperform classical computation so dramatically that the performance itself demands new vocabulary. The next steps are already being mapped. Willow has 105 qubits. Fault-tolerant, general-purpose quantum computing that could tackle the hardest problems in chemistry, materials, science, cryptography, and optimization is estimated to require systems with millions of logical qubits. Qubits that have been corrected and stabilized to the point of near-perfect reliability. The gap between 105 and a million is enormous. But the trajectory is real. The below-threshold error correction that Willow demonstrated is the foundational requirement for everything that comes after. Without it, scaling up just means scaling up the noise. With it, scaling up means scaling up the power. And the implications of that power, when it arrives, are not subtle. Quantum computers at sufficient scale could simulate the behavior of molecules with enough accuracy to design entirely new drugs. Not by trial and error, not by testing thousands of compounds in a lab, but by computing the quantum mechanical interactions of every atom in a target molecule and designing a binding partner from first principles. They could simulate materials with properties that have never been seen in nature, designing superconductors that work at room temperature, or batteries with energy densities that make current technology look primitive. They could break the cryptographic protocols that protect most of the world's digital communications, a fact that has already prompted governments and standards bodies to begin the long process of transitioning to post-quantum cryptography, a race that is already underway, even though the threat is still years from being real. And they could, as the Nature paper from August 2025 demonstrated, simulate the fundamental forces of nature directly, not model them, not approximate them, simulate them. Run the actual quantum mechanical rules on a quantum mechanical substrate, and watch physics happen inside a chip rather than inside a particle accelerator. The scientific implications of that are difficult to overstate, because there are questions in physics that particle accelerators cannot answer. Questions about the strong nuclear force at low energies. Questions about confinement that require computational tools that classical systems cannot provide and that only quantum simulation can offer. This is the real story, not a chip that stopped at the edge of the universe, but a chip that started. That took the first credible steps down a road that physicists have been trying to get on for 40 years. That demonstrated, in controlled experiments published in the most rigorous scientific journals in the world, that quantum computing is no longer a theoretical ambition. It is an engineering reality. The viral story was false, but the instinct behind it, the sense that something enormous is happening, that Google has built something that brushes up against limits we didn't fully understand we had, that instinct is not wrong. It is just pointed at the wrong thing. The mystery is not that the chip stopped. The mystery is that it started. That against all the engineering obstacles, all the decoherence, all the fragility, all the decades of failed attempts and overstated claims, someone finally built a quantum processor that works, that crosses the error correction threshold, that can simulate gauge theories, that can reveal topological phases of matter, that performs in under 5 minutes a calculation that classical computers cannot complete in the entire remaining life of the sun. That is the real story. And it is, when you sit with it honestly, far stranger and far more significant than any viral rumor about a mysterious halt. Because a machine stopping is an ending. What Willow represents is a beginning, and beginnings, when they are genuine, when they are real, when they are backed by equations and experiments and peer review and published data, are always more consequential than endings. Endings are finite. Beginnings open doors that you cannot see the end of from where you are standing. We are standing at one of those doors right now, and whatever is on the other side of it, whether it is new medicines or new materials or new understanding of the forces that hold reality together, or whether it is, eventually, someday, a genuine encounter with the computational limits of physical law itself, we are only at the threshold. The chip did not stop. It is still running. And if the people building these machines are right about where this road leads, what comes next will make the viral story look small. Not because the viral story was dramatic, but because the truth, as it almost always is more dramatic still. And that is what separates this moment from every previous announcement about quantum computing. Every previous claim of supremacy, every previous headline about qubits and entanglement and computing power beyond imagination came with an asterisk, a caveat, a yes but. Yes, it performed this task faster, but the task was artificial. Yes, it demonstrated quantum advantage, but only on a benchmark it designed itself. Yes, it showed error reduction, but not at scale. Willow has not eliminated those caveats entirely, but it has answered the most fundamental one. It has proven that the physics works, that below-threshold error correction is not a theoretical possibility. It is a demonstrated reality, and in the history of technology, that transition from possible to demonstrated is the one that changes everything. Once something has been shown to work, the only question remaining is how fast it can be built bigger, and the people building it have no intention of slowing down. The real question is not whether Google's quantum chip stopped at the edge of reality. The real question is what happens when machines like this one are 10 times larger, 100 times more stable, and pointed at the problems that have resisted every tool humanity has ever built. We do not know the answer, but for the first time, we have a machine capable of beginning to find out. And that, quietly, is one of the most significant things that has happened in the history of science.